When you look up at the night sky and see the distant pinpoints of light scattered across the darkness, you're witnessing something profound and deeply unsettling. Those stars, those galaxies, those cosmic beacons aren't just far away in the conventional sense. They're separated from us by something far more absolute than mere distance. They're isolated by time itself, locked behind a barrier more impenetrable than any wall humanity has ever encountered. The speed of light, often celebrated as the fastest thing in existence, turns out to be cosmically slow, a crawling messenger that takes eons to bridge the voids between worlds. We've grown comfortable with the idea that light is fast. After all, flip a switch and the room floods with illumination instantly, or so it seems. Light crosses the span of a room in billionths of a second, too quick for human perception to notice any delay. Even at planetary scales, light seems adequately swift. A signal from Earth reaches the moon in just over a second. The sun's light takes about 8 minutes to warm our faces. These are manageable timescales, comprehensible to our everyday experience. But this comfort evaporates the moment we begin to contemplate the true scales of the cosmos. The nearest star system to our own, Alpha Centauri, sits roughly 4 light-years away. 4 years for light itself to make the journey. If we somehow sent a message to hypothetical neighbors living on a planet orbiting those stars, we'd wait 4 years for our greeting to arrive, and another 4 years for any response. That's an 8-year conversation with our closest stellar neighbors, but Alpha Centauri is practically in our backyard on cosmic scales. Most stars we see with the naked eye are hundreds or thousands of light-years distant. The beautiful spiral arms of our Milky Way galaxy stretch across approximately 100,000 light-years. The Andromeda Galaxy, the nearest large galaxy to our own, floats 2.5 million light-years away. These numbers become almost meaningless to human intuition. We can write them down, calculate with them, plot them on graphs, but truly grasping what they mean for lived experience requires a shift in perspective. When you see Andromeda in a telescope, you're not seeing it as it exists right now. You're seeing it as it was 2.5 million years ago, when our ancestors on Earth were just beginning to chip stone tools with deliberate purpose. The light that entered your eye tonight began its journey before humans as we know ourselves existed. Andromeda could have exploded in some cosmic catastrophe 1 million years ago, and we'd continue to see it as serene and unchanged in our sky for another 1.5 million years. This isn't just an interesting quirk of astronomy. It's a fundamental constraint on how we can interact with the universe. The speed of light doesn't just limit how fast we can see things, it limits how fast anything can happen, how quickly information can travel, how rapidly cause and effect can propagate through space. Einstein's special relativity revealed that the speed of light in vacuum, approximately 299,792 kilometers per second, isn't just the speed of light. It's the speed of causality itself, the maximum rate at which any influence can pass from one point to another. Nothing with mass can reach this speed, let alone exceed it. As objects accelerate closer to the speed of light, they require exponentially more energy to gain each additional increment of velocity. The mass appears to increase, time slows down relative to stationary observers, and lengths contract in the direction of motion. Reaching the speed of light would require infinite energy, placing it forever beyond the realm of possibility for anything made of ordinary matter. Light itself moves at this ultimate speed only because photons have no mass at all. They're ripples in electromagnetic fields, forever locked at exactly this cosmic speed limit from the moment of their creation to their eventual absorption. This creates a strange, counterintuitive universe. Imagine you're aboard a spacecraft accelerating through space, pushing closer and closer to the speed of light. From your perspective inside the ship, you'd feel the acceleration, the force pressing you back into your seat. You could, in principle, keep accelerating indefinitely, always feeling that push, always gaining speed from your own point of view. But observers back on Earth would see something different. They'd watch your ship accelerating rapidly at first, but then the acceleration would appear to slow. You'd approach the speed of light asymptotically, getting closer and closer but never quite reaching it, like a mathematical limit that can be approached but never attained. Meanwhile, because of time dilation, your clock would tick slower and slower from Earth's perspective. A year might pass for you while centuries elapsed at home. This relativistic effect has been confirmed countless times in particle accelerators, where subatomic particles routinely reach 99.9999% of light speed. From the perspective of these particles, hardly any time passes before they slam into their targets. But from our perspective in the laboratory, we can measure their extended lifetimes as time dilation stretches their normally brief existence. The math works perfectly. The predictions match observations with extraordinary precision. There's no doubt that this is how our universe actually operates. For space exploration, these facts impose brutal constraints. Let's consider what it would take to visit even our nearest stellar neighbor. The Voyager probes, humanity's most distant artificial objects, are traveling at roughly 17 kilometers per second relative to the Sun. At that speed, it would take them about 75,000 years to reach Alpha Centauri if they were headed in that direction, which they're not. Even with more advanced propulsion systems, chemical rockets of any conceivable efficiency would require such enormous amounts of fuel to reach even a fraction of light speed that the Enterprise becomes absurd. Most of your spacecraft would be fuel tanks, and you'd spend the first half of your journey accelerating and the second half decelerating so you don't simply fly past your destination at tremendous velocity. More exotic propulsion concepts exist. Nuclear pulse propulsion, where nuclear bombs detonated behind a spacecraft push it forward with their explosions, could theoretically reach perhaps 5% of light speed. That would cut the journey to Alpha Centauri down to about 80 years, still a lifetime, but potentially manageable for a generation ship. Ion drives and other electric propulsion systems offer excellent fuel efficiency, but produce tiny amounts of thrust, meaning they require years or decades of continuous operation to build up significant speed. Solar sails, and pushed by the pressure of sunlight or powerful lasers beamed from Earth, could potentially reach 10 or even 20% of light speed given enough development. But even at 20% of light speed, Alpha Centauri remains 20 years away. These timescales fundamentally change the nature of exploration. We're not talking about voyages of discovery where bold explorers return home with tales of strange new worlds. We're talking about one-way journeys into the cosmic deep. Expeditions where the travelers would spend their entire lives in transit, where maintaining a viable human society inside a spacecraft for decades becomes as important as the destination itself. Even communication becomes an exercise in patience. Ground control can't offer real-time guidance when the speed of light enforces delays of years. Each message from home arrives as a time capsule, news from a world that has already moved on. Expand the scale beyond our stellar neighborhood, and the situation becomes even more stark. The Milky Way contains somewhere between 100 and 400 billion stars, spread across that 100,000 light-year disk. The galaxy's sheer size means that even if we could travel at 90% of light speed, which remains firmly in the realm of science fiction, crossing from one spiral arm to another would take tens of thousands of years of subjective time. Mapping the entire galaxy through direct exploration would require millions of years. By the time explorers returned from the far side of the galactic disk, assuming they could somehow send messages back, the civilization that launched them would have evolved beyond recognition or disappeared entirely. This begins to reveal something profound about our cosmic situation. We exist within bubbles of possible interaction, regions of space and time where we can realistically affect events and receive information. Your personal bubble of interaction is quite small, limited by human lifespans and travel times. Even at the scales of nations, the bubble extends only so far. Humanity as a whole has a larger bubble, but it's still minuscule compared to the galaxy, and laughably tiny compared to the observable universe as a whole. And the Milky Way, vast as it seems, is just one galaxy among trillions in the observable universe. The universe extends for at least 93 billion light-years in diameter, though that figure needs careful unpacking. When we say the observable universe is 93 billion light-years across, we're not saying we can see 93 billion light-years in every direction based on the age of the universe. The universe is only about 13.8 billion years old, so light has only had 13.8 billion years to reach us from distant sources. But during that time, space itself has been expanding, carrying distant objects away from us. The most distant objects we can see, whose light has been traveling for 13.8 billion years, are now about 46.5 billion light-years away due to this expansion. The light we see left them when they were much closer. but they've since receded into the cosmic distance. This expansion of space introduces a complication that makes intergalactic travel even more daunting than simple distance suggests. Galaxies aren't just sitting in space at fixed locations, they're embedded in space, and space itself is growing, stretching like the surface of an inflating balloon. For nearby galaxies, this expansion is minimal, easily overwhelmed by local gravitational attraction. The Andromeda Galaxy, for instance, is actually moving toward the Milky Way, and the two galaxies will eventually collide and merge billions of years from now. Gravity keeps local groups of galaxies bound together, but look beyond the local group to distant galaxies, and expansion takes over. The farther away a galaxy is, the faster it appears to recede from us, not because it's moving through space, but because the space between us and that galaxy is expanding. This relationship, described by Hubble's law, means that sufficiently distant galaxies are receding faster than light. This doesn't violate relativity because nothing is actually moving through space faster than light. Space itself is expanding, carrying galaxies along with it. From the perspective of anyone in those distant galaxies, they're perfectly stationary, and we're the ones receding into the distance. There's a boundary, a cosmic horizon beyond which galaxies are receding faster than light. Light from galaxies beyond this boundary can never reach us, no matter how long we wait, because the space between us expands faster than light can cross it. It's like trying to swim upstream in a river flowing faster than you can swim. You make progress through the water, but the water itself carries you backward, and you make no net progress toward your destination. This horizon defines the observable universe, the region of space from which light has had time to reach us since the Big Bang. But there's another, more troubling horizon. As the universe continues to expand, and that expansion appears to be accelerating due to dark energy, galaxies beyond our local group will eventually recede beyond the cosmic event horizon. This is the boundary beyond which we can never send a signal that will reach its destination. A galaxy sitting just beyond this horizon is receding fast enough that any light we send toward it will never close the gap. The expanding space between us and the distant galaxy stretches faster than our signal can cross it. Current estimates suggest that about 94% of the observable universe is already beyond this event horizon. We can see these distant galaxies because we're looking at ancient light they emitted billions of years ago when they were closer, but we could never reach them, never send them a message, never affect them in any way. They're forever isolated from us, entire galaxy superclusters containing hundreds of trillions of stars and presumably countless planets, permanently beyond any possibility of contact. The remaining 6% of the observable universe, the galaxies within our cosmological event horizon, seems more accessible. But even here, the numbers are intimidating. The nearest large galaxy cluster beyond our local group, the Virgo cluster, lies about 65 million light-years away. Even if we could somehow travel at 99.99% of light speed, the journey would take tens of millions of years from Earth's perspective. Time dilation would slow clocks aboard the spacecraft significantly, so travelers might experience less time subjectively, but they'd still be undertaking a journey measured in megayears. And here's where cosmic expansion adds insult to injury. During the millions of years such a journey would require, space would continue expanding. The distance to your destination would literally increase while you traveled. At the speeds we're discussing, this effect is relatively minor for nearby targets like Andromeda, but for more distant galaxies, expansion becomes a significant factor. There may come a point where even traveling at near light speed isn't enough to overtake the expansion of space itself. You'd be racing against the expansion of the cosmos, and the cosmos might win. The implications extend beyond simple distance. Consider that the observable universe has a finite radius of about 46 billion light-years, not because nothing exists beyond that boundary, but because light from regions farther away hasn't had time to reach us since the Big Bang. More troubling still, galaxies beyond our local group are receding from us faster than light could ever carry us toward them. The universe is partitioned into isolated islands, and we're stuck on ours. Future civilizations, billions of years from now, might look up at a night sky devoid of distant galaxies, those cosmic neighbors having receded beyond the observable horizon. They'd peer into darkness and perhaps conclude they were alone in all existence. This cosmic isolation creates a peculiar temporal prison as well. When astronomers observe distant galaxies, They're not seeing those galaxies as they currently exist, but as they were millions or billions of years ago. As the galaxy you're admiring through a telescope might have already collided with another galaxy, spawned countless new stars, or been torn apart by gravitational forces, you'd have no way of knowing. The light carrying that information is still making its way through the void, and it won't arrive for eons. We're perpetually looking at history, never at the present state of the distant cosmos. The universe we observe is essentially a vast museum of the past, with exhibits arranged according to their distance from us. This temporal disconnect affects how we understand causality itself. Events happening right now in distant galaxies will only become observable to us in the far future. Meanwhile, events we're witnessing from those same galaxies occurred in the ancient past. There's no universal now that extends across the cosmos. Einstein's relativity made this clear by showing that simultaneity depends on your reference frame. Two observers moving at different velocities will disagree about whether two distant events occurred at the same time. The concept of a shared present moment spanning the universe simply doesn't exist in any meaningful physical sense. For practical purposes, this means that any truly vast cosmic civilization would be fundamentally fragmented. Imagine a hypothetical empire spanning multiple galaxies. By the time a message from the capital reached a distant province, millions of years would have passed. The government that sent the message would have risen and fallen countless times. The language, culture, and technology would have evolved beyond recognition. The entire concept of a unified civilization across such distances becomes almost meaningless. Each isolated region would effectively be living in its own timeline, connected to others only through the faint echoes of ancient transmissions that might carry information millions of years out of date. This presents philosophers and ethicists with interesting dilemmas. If you discovered that a catastrophe was unfolding in a distant galaxy, something you could observe through your telescopes, what moral obligation would you have to respond? The disaster happened millions of years ago in real time, even though you're just witnessing it now. Any help you might send would take millions more years to arrive. By the time your rescue mission reached that galaxy, the civilization that suffered might have recovered, or evolved into something unrecognizable, or gone extinct. You'd be sending help to a version of that civilization that no longer exists, based on a catastrophe that finished playing out in the distant past. The speed of light limitation also fundamentally constrains how we can conduct science. Experiments at particle accelerators must account for the finite speed at which signals propagate. When you're smashing particles together at near light speed, the timing of detector readings becomes crucial, and the speed of light introduces delays that must be precisely calculated. In astronomy, parallax measurements that help us determine stellar distances depend on observations taken 6 months apart, when Earth is on opposite sides of its orbit. But even that baseline of about 300 million kilometers is laughably small on cosmic scales. For more distant objects, we rely on indirect methods, building up chains of inference that become increasingly uncertain as we peer deeper into space. The finite speed of light also means we can't easily test certain cosmological theories. If you wanted to verify some prediction about the structure of the universe on the largest scales, you might need to wait millions or billions of years for light from the relevant regions to arrive. Some experiments effectively can't be performed within a human lifetime, or even within the lifetime of our species. We're forced to construct theories based on the limited information available to us, always aware that vast portions of the universe remain beyond our observational reach, potentially harboring phenomena that could overturn our carefully constructed models. Even our attempts to map the universe face severe limitations. Creating a three-dimensional map of cosmic structure requires measuring distances to millions of galaxies, but those measurements represent different moments in time. The map you create is really a four-dimensional slice through space-time, showing objects as they appeared at various points in history, depending on their distance. It's like trying to create a snapshot of a constantly evolving system where different parts of the image were captured at wildly different times. The map is valuable, but fundamentally differs from what we'd ideally want, which is a representation of how everything exists right now, something the laws of physics forbid us from obtaining. The communication delays imposed by light speed would affect not just message transmission, but also the development of culture and knowledge. If humanity ever does establish multiple settlements across different star systems, each colony would evolve independently to a large degree. Scientific discoveries made in one system would take years to reach others. By the time news of some breakthrough arrived, the receiving colony might have independently discovered the same thing, or moved on to different research priorities. Rather than a unified human civilization sharing knowledge in real time, you'd have a loose confederation of related cultures, each following its own trajectory, connected only through time-lagged correspondence. This fragmentation might even affect the evolution of science itself. Different colonies might develop different theoretical frameworks, different experimental techniques, different priorities for research. When their findings finally reached each other, they'd need to reconcile competing models and methodologies that had developed in isolation. The unified scientific enterprise we currently take for granted, with researchers around the world collaborating in real time, would fracture into separate traditions. Reunification of knowledge would be an ongoing project, constantly lagging behind the pace of discovery. Consider also the psychological impact of these constraints. Humans are social creatures who crave connection and shared experience. The idea of sending a message and not receiving a reply for decades or centuries is profoundly alienating. Would people bother maintaining communication with distant colonies knowing they'd likely die before hearing back? Would the concept of a unified human identity persist when practical interaction becomes impossible? These aren't just technical challenges, but existential questions about the nature of community and belonging in a universe that seems designed to keep us apart. The speed of light also creates strange scenarios involving information and causality. Imagine a future where we've detected an inhabited planet 30 light-years away. We pick up their television broadcasts, watch their shows, study their culture, but everything we're seeing happened 30 years ago. We're viewing their past, a society that has already moved on, changed, perhaps even ended. If we sent them a message, it would take 30 years to arrive, and their reply would take another 30 years to return. By the time we're having a conversation, 60 years will have passed. The people who sent the original message might be long dead. You'd be corresponding with civilizations in a strange asynchronous dance, each side responding to ghosts from the other's past. This asymmetry becomes even more pronounced if the civilization you're communicating with is at a different technological level. Suppose you're a highly advanced society communicating with one that's just achieved radio capability. You send them information about advanced physics, medical treatments, engineering techniques. 30 years later, you receive their reply, thanking you for information that is now outdated from your perspective, but revolutionary from theirs. You send more updates. But by the time those arrive, their society has evolved. Perhaps they've independently discovered some of what you sent. Perhaps they've taken a different technological path. The conversation becomes increasingly difficult to maintain coherently. Some theorists have proposed using these light-speed delays for creative purposes. Since information can't travel faster than light, you could theoretically create zones that are causally disconnected from each other, at least temporarily. If you wanted to conduct an experiment where one group couldn't possibly be influenced by another, you could separate them by enough distance that no signal could travel between them in the time available. Such setups have been used in quantum mechanics experiments, testing Bell's inequalities, ensuring that measurements on entangled particles couldn't influence each other through any conventional signal. The speed of light becomes a tool for enforcing isolation when needed. But quantum entanglement itself introduces another fascinating wrinkle in our discussion. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. This seems to violate the light speed limit, suggesting that information could be transmitted instantaneously. However, the situation is more subtle than it first appears. While the correlation between entangled particles is indeed instantaneous, you can't use this phenomenon to actually transmit information faster than light. The measurement results on one particle appear random until you compare them with the results from the other particle. That comparison requires classical communication, which remains limited by light speed. Quantum mechanics teases us with hints of faster-than-light phenomena, but ultimately enforces the cosmic speed limit when it comes to useful information transfer. This hasn't stopped physicists from exploring whether quantum effects might offer loopholes. Various proposals have suggested using entanglement, quantum teleportation, or other quantum phenomena to circumvent light speed restrictions. So far, all these proposals either don't actually allow faster-than-light communication or rely on effects that haven't been experimentally verified and may be impossible. The universe appears quite determined to enforce its speed limit. Though every apparent loophole discovered so far has turned out to be a dead end or a misunderstanding of the physics involved. The constraints go deeper still when we consider the nature of space-time itself. General relativity describes space and time as a unified fabric that can be curved by matter and energy. Light travels along the shortest possible paths through this curved space-time, paths called geodesics. When we say nothing can travel faster than light, we mean nothing can take a shortcut that would let it beat a light beam traveling on a geodesic between the same 2 points. This is a fundamental statement about the geometry of space-time, not just about the properties of light itself. However, general relativity does permit some exotic possibilities that might seem to violate the spirit of the light speed limit, even if they don't violate its letter. The Alcubierre drive concept imagines contracting space in front of a spacecraft while expanding it behind, creating a warp bubble that carries the ship along. From an external perspective, the ship might cross distances faster than light, but within the bubble, it's not actually moving through space faster than light. The space itself is moving. The ship surfs on a wave of space-time curvature. Unfortunately, the Alcubierre drive requires exotic matter with negative energy density, something we've never observed and which may be forbidden by quantum field theory. Even if such matter exists, the energy requirements appear astronomical, potentially requiring the mass energy of entire planets or stars. More troublingly, the interior of the warp bubble would be causally disconnected from the exterior, meaning the pilot couldn't actually control where the ship goes or turn the drive on or off while it's active. You'd need to pre-program your journey and hope nothing goes wrong, with no ability to adjust course once underway. Other proposals involve wormholes, theoretical tunnels through space-time that connect distant regions. If you could create and stabilize a wormhole, you might step through and emerge light years away, having traveled only a short distance through the wormhole itself. Again, the light speed limit isn't technically violated since you're not moving through normal space faster than light. You're taking a shortcut through a different topology of space-time. But wormholes also require exotic matter to remain stable and open. Such without it, they'd collapse immediately, crushing anything trying to pass through. Additionally, traversable wormholes raise serious causality issues, potentially allowing time travel and the paradoxes that come with it. These speculative solutions highlight how desperately we'd like to escape the light speed constraint. We've constructed elaborate theoretical frameworks that might permit faster-than-light travel while technically respecting relativity's rules. Yet every scheme requires phenomena we've never observed, energies we can't harness, or technologies we can't imagine building. The universe seems to place the solution just barely out of reach, like a cruel cosmic joke. Perhaps there's a deeper principle at work, some reason why faster-than-light travel must remain impossible beyond the difficulties already identified. Some physicists suspect that allowing faster-than-light travel would fundamentally break causality, creating situations where effects precede their causes. In relativity, faster-than-light motion in space is equivalent to backward time travel in certain reference frames. If you could send information faster than light, you could construct scenarios where messages arrive before they're sent, creating causal loops and paradoxes. The universe might be protecting itself from such inconsistencies by making the light speed barrier absolute. Causality itself may demand that nothing travels faster than light. The philosophical implications are profound. We imagine ourselves as beings capable of understanding and eventually mastering nature. Yet here's a fundamental limitation that may be absolute and eternal. No amount of technological progress, no clever engineering, no brilliant insight can overcome it if the barrier is truly fundamental. We're confined to our cosmic neighborhood, limited to observing distant regions only through ancient light, forever prevented from directly experiencing most of the universe. It's a humbling realization, suggesting that our ambitions may always exceed our reach. This limitation also affects how we think about potential alien civilizations. If advanced aliens exist, they face the same constraints we do. They can't easily travel between galaxies, can't maintain real-time communication across vast distances, can't explore more than a tiny fraction of the cosmos. Any truly ancient civilization would have had billions of years to spread throughout the universe, yet we see no evidence of such expansion. So perhaps the light speed limit effectively quarantines civilizations, keeping them confined to their local regions. The Fermi paradox, which asks why we haven't detected aliens despite the vast number of potentially habitable worlds, might be partially answered by recognizing that interstellar travel is difficult enough that even advanced civilizations rarely attempt it. Alternatively, maybe civilizations that achieve interstellar capability tend to send out probes or colonies that then evolve independently, losing contact with their origin world. By the time such colonies have spread significantly, they might no longer resemble the civilization that created them. The galaxy could be populated by countless isolated pockets of intelligence, each unaware of the others, each evolving along its own path. Yeah, we might have neighbors just a few hundred light years away, civilizations roughly as advanced as ourselves, but we'll never know about them because the distances and time delays make communication and travel impractical. Some researchers have proposed that advanced civilizations might overcome biological limitations through technology, perhaps uploading their minds into computers or extending their lifespans indefinitely. Such beings might find interstellar travel more feasible since they wouldn't mind spending centuries or millennia in transit. A digital consciousness might not experience time the same way we do and could simply enter a dormant state during long journeys, awakening upon arrival. But even for such beings, the light speed limit remains. They'd still need to cross the vast gulfs between stars, and still need to wait years for messages from home. The constraints change in magnitude, but not in kind. The isolation imposed by light speed becomes even more severe when we consider the expansion of the universe itself. Space isn't static. It's been expanding since the Big Bang, and most remarkably, this expansion is accelerating. When we look at distant galaxies, we're not just seeing them as they were in the past because of light travel time. We're also watching them recede from us, carried away by the expansion of space itself. This expansion doesn't just make the universe bigger, it fundamentally changes which parts of the universe we can ever hope to reach or communicate with. There's a boundary called the cosmic event horizon, beyond which galaxies are receding faster than light could ever catch up. This doesn't violate relativity because it's not the galaxies moving through space faster than light. Instead, it's space itself expanding between us and them. For any galaxy beyond this horizon, no signal we send today will ever reach them. Even if we sent a message at light speed right now, the expanding space would stretch it out, slowing its progress relative to the galaxy we're trying to reach until it could never close the gap. These galaxies are causally disconnected from us. Nothing we do will ever affect them. Nothing they do can ever reach us. They exist in our past light cone, meaning we can see their ancient light, but they don't exist in our future light cone. We're already saying goodbye to them without knowing it. As the universe continues to expand and accelerate, but more and more galaxies will cross this threshold. In the far future, observers in our galaxy will look out and see fewer galaxies than we see today. Eventually, in trillions of years, other galaxies will have receded so far that their light will be redshifted into invisibility. Civilizations arising then, if any do, will look at the sky and see only their own galaxy surrounded by darkness. They'll have no way to know that billions of other galaxies once populated the cosmos. The evidence will have literally moved beyond their reach. The universe will have expanded their observable universe down to just their local group. It's a profoundly lonely thought. The cosmos itself will have hidden most of its own history from future observers. Even within what we can currently see, the vast majority of galaxies are functionally unreachable. The observable universe extends about 46 billion light-years in every direction. That's bigger than you might expect for a universe that's only about 14 billion years old, and it's precisely because of cosmic expansion. Light from the most distant galaxies has been traveling for most of the age of the universe, but during that time, space itself has been expanding, carrying those galaxies even farther away. By now, the galaxies that emitted the light we're just receiving today are actually more than 40 billion light-years away. If we tried to reach them, even traveling at light speed, we'd never get there. They're receding too fast. The expansion of space creates a fundamental limit on the volume of the universe we could ever explore, even in principle. And within our local group of galaxies, things are different. Gravity holds nearby galaxies together strongly enough to overcome cosmic expansion. The Andromeda Galaxy, for instance, is actually moving toward us and will collide with the Milky Way in about 4 billion years. Our local group, containing the Milky Way, Andromeda, and about 50 smaller galaxies, is gravitationally bound and will eventually merge into a single enormous galaxy. These galaxies remain accessible to us in principle, assuming we could survive billions of years and develop the technology for intergalactic travel. But beyond our local group, space expansion dominates, and almost everything is slipping away from us forever. This means that the scope of possible exploration, even for an incredibly advanced civilization, has hard limits. But you could imagine a species that colonizes their entire galaxy. You could imagine them sending generation ships to nearby galaxies in their local group over millions of years. But you can't imagine them spreading throughout the universe. Most of the universe is simply off-limits, sealed away by expanding space. The cosmos has drawn a boundary around what's possible, and no amount of technological advancement can change that fundamental constraint. We're confined to our local cosmic neighborhood, and that neighborhood is tiny compared to the whole universe. Even communicating within our own galaxy presents enormous challenges due to light speed. The Milky Way is about 100,000 light-years across. If we sent a message to a civilization on the far side of the galaxy, it would take 100,000 years to reach them. And their reply would take another 100,000 years to come back. That's a round-trip time of 200,000 years, longer than our species has existed. Any dialogue would be impossible. We could only send declarations, time capsules of information with no expectation of response within any meaningful time frame. Imagine you detected a signal from an intelligent civilization 50,000 light-years away. The message you're receiving was sent when Neanderthals still walked the Earth. In the time since they sent it, their entire civilization could have risen, flourished, and gone extinct. By the time your reply reaches their planet, you have no idea if anyone will be there to receive it, or what state their society might be in if they still exist. You're not having a conversation. Yet you're exchanging messages with ghosts, reaching across such vast stretches of time that you're essentially communicating with the past and future rather than the present. This temporal dimension of space travel fundamentally changes what exploration means. On Earth, explorers could go somewhere, make discoveries, and bring news back. They maintained a connection to home, even if messages took months or years to travel. But in space, particularly as distances grow, the connection becomes increasingly theoretical. A ship traveling to a star 20 light-years away wouldn't just be 20 years of travel time from Earth. By the time it arrived and sent a message back, 40 years would have passed on Earth. Everyone who watched the ship depart would be 40 years older or dead. The civilization itself would have changed. And technologies would have advanced. Political systems might have transformed. The explorers would be stepping into a future they never experienced, having aged only 20 years while their home world aged 40. This creates a strange asymmetry. Time dilation means astronauts traveling at high speeds age more slowly than people at home. At 99% of light speed, time dilation is significant enough that travelers age about 7 times more slowly than people at rest. A journey that takes 40 years from Earth's perspective might feel like only 6 years to the crew. They'd return to find that everyone they knew was 40 years older, that they'd skipped decades of history and technological change. They'd be time travelers of a sort, strangers in their own future. This is sometimes called the twin paradox. Though it's not actually a paradox. It's a real effect of relativity that makes high-speed space travel a one-way ticket, not just spatially, but temporally. You can't really go home again because home will have moved on without you. For civilizations attempting to coordinate activities across a galaxy, these time delays create nearly insurmountable problems. How do you maintain a coherent society when different parts of it are separated by decades or centuries of communication time? How do you make collective decisions when getting everyone's input takes thousands of years? The answer is probably that you don't. A galaxy-spanning civilization, if such a thing could exist, wouldn't be unified in any meaningful sense. It would be a collection of isolated colonies that share a common origin but evolve independently. Each colony would develop its own culture, technology, and political systems. They might exchange information when messages arrived, but they couldn't coordinate actions or maintain shared governance. The light speed limit would fracture any attempt at unity. Some scientists have proposed that advanced civilizations might use networks of autonomous probes to explore the galaxy. These von Neumann probes would be self-replicating machines programmed to travel to nearby star systems, build copies of themselves from local materials, and send those copies on to other stars. Over millions of years, such a network could theoretically spread throughout the galaxy, with each probe sending data back to the homeworld. Even then, the civilization would be viewing information from thousands or millions of years in the past, creating a patchwork map of the galaxy as it was at wildly different times. The center of the galaxy would be visible as it was 30,000 years ago, while nearby stars would show up almost in real time. It would be like looking at a photograph where different parts of the image were taken at completely different moments in history. The speed of light also constrains our ability to respond to threats or opportunities discovered far away. If we detected an asteroid on a collision course with a distant colony, our warning message would take years to arrive, by which time the impact might have already occurred. If colonists discovered a valuable resource or a dangerous phenomenon, they'd have to wait years for instructions or assistance. Every outpost would need to be functionally autonomous, capable of making all critical decisions without input from anyone else. The colony wouldn't just be distant in space. It would be isolated in time, living in a delayed present where help couldn't arrive and information couldn't travel faster than light's patient march. These constraints raise interesting questions about whether we should even try to send humans into deep space. Robotic probes don't care about isolation or time dilation. They don't get lonely or homesick. They can be put into hibernation during long journeys and awakened at their destination. They can operate for decades or centuries without psychological strain. For purely scientific exploration, robots make far more sense than humans. They're cheaper, more durable, and don't need life support. They don't worry about never seeing home again, or about returning to find everyone they knew has died. And the case for human space exploration to distant stars is harder to make when you consider the psychological and social costs alongside the enormous technical challenges. Yet there's something about human exploration that feels important beyond pure practicality. Sending robots to explore the universe is like reading about places rather than visiting them. The experiences aren't the same. There's a qualitative difference between viewing Mars through the eyes of a robot and having a human stand on its surface, even if the data collected is similar. Perhaps more importantly, colonization requires humans, or at least biological beings, if we're serious about establishing humanity as a multiplanetary or multistellar species. Robots can explore, but they don't establish civilizations. They don't create new homes for humanity. If we want to spread beyond Earth, not just study what's out there, we eventually need to send people with all the complications that entails. This brings us to one of the most profound implications of light speed limits. They don't just constrain travel and communication, they shape the very structure of possible civilizations. On Earth, human civilization has become increasingly interconnected. We can communicate instantly with people on the other side of the planet. We trade goods, share ideas, coordinate actions, and think of ourselves as part of a global community. This interconnection shapes everything from economics to culture to politics. But this model of civilization simply cannot extend beyond Earth once distances grow large enough. The light speed limit enforces decentralization, and it makes true galactic empire impossible, at least in the traditional sense of a unified political entity with centralized control. Any attempt at a galaxy-spanning empire would face the problem that orders from the capital would arrive outdated by decades or centuries. Local governors would have to act independently because they couldn't wait for instructions. Over time, this independence would naturally evolve into autonomy and eventually full separation. The parts of the empire would drift apart, not just physically, but culturally and politically. They might maintain sentimental connections, might exchange knowledge and history, but they couldn't function as a single, coherent entity. The light speed limit makes decentralization and local autonomy inevitable for any civilization that spreads across the stars. This has surprisingly optimistic implications in some ways. It means that authoritarian control over vast reaches of space is essentially impossible. No dictator could maintain an iron grip on a galaxy-spanning civilization because their orders would arrive far too slowly to micromanage distant worlds. Local populations would have de facto autonomy simply because the physics of the universe makes anything else impractical. On the other hand, it also means that the kind of cooperation and coordination we're used to on Earth couldn't extend to the stars. Each colony would be on its own, unable to call for help when needed, unable to share resources quickly in times of crisis. So the universe enforces a kind of cosmic federalism where local communities must be self-sufficient because distant aid simply isn't available on relevant timescales. We see a hint of this even in our current space program. The Mars rovers operate semi-autonomously because the communication delay between Earth and Mars ranges from about 3 to 22 minutes depending on where both planets are in their orbits. Engineers can't manually drive the rovers in real time. Instead, they send instructions and wait for the rover to execute them and send back results. As we send missions farther out into the solar system, this delay grows. New Horizons, which flew past Pluto, was so far away during its encounter that radio signals took about 4.5 hours to reach Earth. The spacecraft had to execute its entire Pluto flyby autonomously, following pre-programmed instructions, because there was no time for mission control to respond to anything that happened. By the time we learned what the spacecraft was seeing, the flyby was already over. Scale this up to interstellar distances, and you can see why human crews would need complete autonomy. A ship traveling to Alpha Centauri couldn't radio home for advice and wait for a response. Everything would have to be decided by the crew. They'd truly be on their own in a way that's hard to comprehend from our connected world. This level of isolation has no modern parallel. Even Antarctic research stations can communicate with the outside world. Even submarines eventually surface. But a starship would be cut off from Earth in a profound way. Living in a bubble of delayed time where news from home would always be years out of date, and where any crisis would need to be solved without outside help. Some scientists and science fiction authors have speculated about ways around the light speed barrier. The Alcubierre drive is a theoretical concept that would involve contracting space in front of a spacecraft and expanding it behind, creating a bubble that could move faster than light without the ship itself actually exceeding light speed within the bubble. It's a clever idea that doesn't technically violate relativity because the ship wouldn't be moving through space faster than light. Instead, space would be moving around the ship. Unfortunately, the mathematics suggest that creating such a warp bubble would require exotic matter with negative energy density, something we've never observed and aren't sure exists. Even if it does exist, the energy requirements would be astronomical, possibly requiring the mass energy of Jupiter or larger. It's theoretically possible, but so far beyond our current capabilities that it might as well be magic. Wormholes represent another theoretical possibility for faster-than-light travel, or at least for shortening the effective distance between 2 points. A wormhole would be a tunnel through space-time connecting distant locations. If you could create and stabilize a wormhole, you might step through it and emerge light years away instantaneously. Einstein's equations allow for wormholes as mathematical solutions, but creating them would require similar exotic matter with negative energy to hold them open. Without it, any wormhole would collapse instantly. Even more problematic, we have no idea how to create a wormhole in the first place. The energy scales involved likely exceed anything we could generate by many orders of magnitude. Some physicists speculate that microscopic wormholes might form and dissolve constantly at the quantum level, but scaling these up to sizes that could transport people seems impossibly difficult. There's also the question of whether traversable wormholes would create time travel paradoxes. Some solutions to the equation suggest that wormholes could allow travel backward in time, which opens up all sorts of causality problems. You could potentially go back and prevent your own past from happening, creating logical contradictions. While some physicists argue that nature must have some mechanism that prevents these paradoxes, perhaps by making it impossible to create closed time-like curves, or by making traversable wormholes inherently unstable. Others suggest that many worlds' interpretations of quantum mechanics might resolve the paradoxes by having time travelers branch off into different timelines. But all of this remains deeply theoretical and speculative. The sad reality is that despite decades of research into potential faster-than-light mechanisms, we haven't found any convincing path forward. Every proposal requires exotic physics we don't understand, materials we can't create, or energy levels we can't achieve. It's possible that a sufficiently advanced civilization could overcome these obstacles, but it's equally possible that they represent fundamental barriers that no amount of technological advancement can breach. The universe might simply not allow faster-than-light travel, no matter how clever you are. The speed of light might be a true cosmic speed limit, not just a practical one, but an absolute boundary written into the structure of reality itself. If that's the case, if we truly are bound by light speed forever, then we need to adjust our expectations about humanity's future in space. The Star Trek vision of a united galactic federation with ships zipping around at multiples of light speed isn't possible. The reality would be slower, more patient, more isolated. generation ships taking centuries to reach nearby stars, colonies that develop independently. I am maintaining cultural memory of Earth, but evolving into distinct civilizations. Information sharing that's more like historical correspondence than real-time communication. It's a future that requires a different kind of ambition, one focused on planting seeds rather than building empires. There's something bittersweet about these limitations. The universe has given us the ability to see almost everything that's happened since the Big Bang. We can observe galaxies billions of light years away, peer back in time to when the first stars formed, map the cosmic web of structure on the largest scales. The universe has revealed itself to us in exquisite detail, at least in terms of what it looks like and how it evolved, but at the same time, it's placed most of what we can see forever beyond our reach. Now we're like children looking through a toy store window at marvels we can see but never touch. The universe has shown us wonders while simultaneously telling us we can't have them. Yet perhaps this constraint is also a kind of protection. If we could zip around the galaxy at will, colonizing planets with ease, we might repeat all the mistakes of terrestrial colonization on a cosmic scale. We might spread rapidly without thinking carefully about what we're doing, overwhelming any life we encounter, exhausting resources faster than they can regenerate. The light speed limit forces patience and consideration. It makes each voyage precious because they're so difficult. It ensures that any civilization we establish elsewhere must be carefully planned and self-sufficient. It prevents the kind of thoughtless expansion that has caused so much damage on Earth. The isolation imposed by light speed also preserves diversity. If different star systems remain functionally isolated from each other, they'll develop different solutions to problems, different cultural expressions, different technologies. Instead of one homogeneous galactic culture, we might end up with thousands or millions of distinct civilizations, each shaped by their local environment and their particular history. When they do eventually communicate, sharing information across the light years, they'll have unique perspectives to offer each other. The isolation that seems like a limitation might actually enrich the overall development of intelligence in the galaxy. From a different perspective, the cosmic speed limit teaches humility. It reminds us that we're not the center of the universe and that the cosmos doesn't bend to our desires. There are fundamental limits to what's possible, boundaries we can't cross no matter how advanced we become. In a culture that often assumes any problem can be solved with enough technology and determination, the light-speed barrier is a stark reminder that some problems might not have solutions. Some things might be impossible, and we need to make peace with that, rather than assuming we'll inevitably overcome every obstacle. This humility extends to our understanding of the universe itself. Every observation we make is of the past. The farther out we look, the further back in time we see. The Andromeda Galaxy appears as it was 2.5 million years ago. The most distant galaxies we observe existed when the universe was just a few 100 million years old. We're seeing cosmic history unfold, but we have no way to know what those galaxies look like now. They might still exist in similar forms, or they might have changed dramatically. Some might have been destroyed in collisions or consumed by black holes. Others might be home to advanced civilizations. We can't know because the light carrying that information hasn't reached us yet, and won't for millions or billions of years. This creates a strange epistemic situation where we know the universe's distant past in great detail, but are almost completely ignorant of its distant present. The universe we see is like a photograph taken at different times in different places. It's a composite of many presents that never actually coexisted. When we look at a galaxy a billion light years away, we're seeing it as it was a billion years ago. At that same moment in cosmic time, our own region of space looked very different than it does now. The Milky Way we know didn't exist in its current form. There's no perspective from which you could see the universe as it all is right now. The present moment is purely local. Step outside your immediate neighborhood, and you're necessarily looking at the past. This has philosophical implications for concepts like cosmic now or cosmic simultaneity. Special relativity already tells us that simultaneity is relative to your reference frame. Events that appear simultaneous to one observer might not be simultaneous to another observer moving differently. But light speed delays add another layer, making it fundamentally impossible to have knowledge of distant present events. You can only ever know the distant past. The present exists only in principle, not in experience. You can calculate what might be happening now in a distant galaxy, but you can't observe it. By the time you could observe it, it would be the past again. Despite all these limitations and constraints, humanity's attempts to explore space remain deeply meaningful. We're a species that evolved on a single planet, adapted to its specific conditions, yet we've developed the ability to leave that planet and venture into space. We've sent robotic ambassadors to every planet in our solar system and beyond. We've landed on multiple worlds. We've maintained a continuous human presence in orbit for decades. We're planning missions to Mars and beyond. All of this is remarkable, even if it's limited to our tiny corner of the galaxy. The exploration itself, regardless of how far it reaches, represents something important about human nature. We're driven to explore, to understand, to push boundaries even when they're difficult or dangerous. The people working on space missions know about the light speed limit. They understand the vast distances and long timescales involved. They're doing it anyway because the pursuit itself matters. Learning about the universe, reaching beyond our cradle world, testing the limits of what's possible, these activities enrich us as a species, even if we never reach distant stars. There's also the practical consideration that Earth won't last forever. Our sun will eventually exhaust its fuel and expand into a red giant, engulfing the inner planets, including Earth. That's billions of years away, but long before then, the sun's increasing brightness will make Earth uninhabitable. If humanity wants to survive on truly long timescales, we need to become a multi-planetary species and eventually a multi-stellar one. The light speed limit makes this harder, but it doesn't make it impossible. We have time to work on these problems, to develop technologies for long-duration spaceflight, to identify suitable target worlds, to build the infrastructure needed for interstellar colonization. It will take centuries or millennia, but humanity has that time if we don't destroy ourselves first. The projects required for interstellar colonization would be multi-generational by necessity. No single human lifetime could encompass the planning, construction, travel, and establishment of a distant colony. These would be civilization-level projects requiring sustained effort across generations, with people dedicating their lives to work they know they won't see completed. There's something noble in that kind of long-term thinking, in working toward goals that extend far beyond your own life. It's the opposite of the short-term thinking that often dominates modern society. Interstellar colonization would require humanity to think in terms of centuries and millennia, to value outcomes that benefit distant descendants rather than immediate gains. Whether humanity ever accomplishes interstellar travel remains to be seen. The challenges are immense, not just technologically, but socially and economically. And convincing societies to invest enormous resources in projects that won't pay off for generations is difficult. Maintaining the institutional continuity needed to complete century-long missions is hard. Solving all the technical problems of life support, propulsion, radiation shielding, and sustainable habitats is dauntingly complex. Yet humans have accomplished difficult things before. We've built monuments that took generations to complete. We've pursued scientific knowledge purely for its own sake. We've undertaken voyages of discovery knowing many wouldn't return. The drive to explore and expand seems deeply embedded in human culture. Even if we never leave our solar system, understanding the constraints imposed by light speed remains valuable. It shapes how we think about the universe and our place in it. It clarifies what's possible and what isn't, helping us set realistic goals rather than chasing fantasies. It teaches us that the universe operates according to rules we didn't make and can't change, rules we need to understand and work within. The cosmos is neither hostile nor friendly to our ambitions. It simply is what it is, and we need to adapt ourselves to reality rather than expecting reality to accommodate us. The speed of light, in the end, is more than just a physical constant. It's a fundamental feature of space-time that shapes causality, limits information flow, and structures the relationships between events. It ensures that causes precede effects, that information can't propagate instantaneously, that the universe has a comprehensible structure rather than descending into paradox. A universe without a speed limit would be a very strange place, one where causality might break down, and where the logical relationships we depend on might not hold. The light speed limit, frustrating as it is for our ambitions to explore, might be necessary for a universe that makes sense and can support intelligent life in the first place. As we look up at the night sky and contemplate the vast distances between stars, between galaxies, between the structures of the cosmos, we're confronted with both our insignificance and our uniqueness. We're tiny creatures on a small planet, in an ordinary solar system, in an unremarkable galaxy, in a universe containing hundreds of billions of galaxies. The scales are so vast that our entire history, everything humans have ever done, amounts to less than a flicker on cosmic timescales. So, yet we're also unique in our ability to comprehend these scales, to understand the physics that governs the universe, to look back at the Big Bang and forward to the far future. We're the universe becoming aware of itself, at least in our little corner. That's worth something, even if we can't travel freely throughout the cosmos. The light speed limit is a reminder that the universe is bigger and more mysterious than we can fully grasp. We've learned so much in just a few centuries of modern science. We understand the fundamental forces, the basic structure of matter and energy, the evolution of the cosmos from its earliest moments. But we're still at the beginning of understanding dark matter and dark energy make up most of the universe, and we don't know what they are. Like, we don't fully understand quantum mechanics or how to reconcile it with general relativity. We don't know if the universe is finite or infinite, whether other universes exist, what happened before the Big Bang, if that question even makes sense. The speed of light, as frustrating as its limits are, is part of a cosmos full of profound mysteries that will take many more centuries to unravel. Perhaps one day, we'll find a way around the light speed barrier. Perhaps some deeper understanding of physics will reveal mechanisms we haven't imagined yet. Perhaps civilizations far older and wiser than ours have solved these problems, but perhaps not. Perhaps we're already seeing reality as it fundamentally is, and the limitations are real and permanent. Either way, the universe we inhabit is magnificent and worth exploring to whatever extent we can. The night sky full of stars and galaxies, each one a sun with its own story, remains beautiful regardless of whether we can visit them. Understanding the cosmos, learning its secrets, pushing the boundaries of knowledge, these pursuits have value in themselves, whether or not they lead to practical applications. Humanity stands at an interesting moment. We've left our planet, but barely. We've learned enough physics to understand the enormous challenges of interstellar travel, but not enough to know if solutions exist. We're like early hominids who've just learned to make fire, standing at the edge of a vast wilderness we're only beginning to explore. The journey ahead is long and uncertain. The speed of light ensures it will be slow and difficult. But it's a journey worth taking, one step at a time, one discovery building on another, one generation passing knowledge to the next. The universe may be vast and mostly unreachable, but the small part we can explore contains wonders enough to occupy us for millennia to come.